Points of inflection. If the graph of a continuous function has a tangent line at a point, possibly a vertical line, and the graph changes concavity at that point, then it changes from concave upward to downward or vice versa, then the point is called a point of inflection. Hypercritical values of x are those values x equals c in the domain where f double prime at c equals 0 or f double prime at c doesn't exist. To determine points of inflection. Step 1, find the second derivative. Step 2, find the hypercritical values of x by looking at two different cases. The first case, f double prime at c equals 0. Second case, f double prime at c is undefined. And step 3, using the hypercritical values as endpoints of the intervals, determine the intervals where the f double prime greater than 0 and f is concave upward. For case B, f double prime or the second derivative less than 0 or f is concave downward. And the point of inflection occurs at those hypercritical values where f changing the concavity from positive side to negative side or from negative side to positive side, or changing from concave up to concave down or concave down to concave up. Like this example, at point C, on the left side, the graph is concave upwards. The right side, the graph concave downward. So the point of inflection occurs at C because the f double prime changing the sign from positive to negative, which is similar to the graphical B. At the point C1, the left side of the point C1, the graph is concave upward. The right side concave downward. And at the point C2, the left side concave downward, the right side concave upward. So point C2 is also the point of inflection. And we call the point C1, C2 as a hypercritical value. Let's look at the example. For the function f of x equals x to the third minus 3 over 2 x squared plus 5, part A, determine the intervals on which f is concave upwards and the interval on which it is concave downward. And then part B, locate any inflection points. For part A, to determine the intervals that the function concave up or concave downwards, so we find the second derivative. First of all, we're going to find f prime, which is 3x squared minus 3 times x, and then find the second derivative as 6x minus 3. Find the hypercritical value. Where f double prime equals 0, or where 6x minus 3 equals 0, and solve for x, we get x equals 1 over 2. Now we have the hypercritical value 1 over 2. We determine the sign of f double prime. The right interval of the 1 over 2, if you replace the f double prime, replace x in the f double prime as the value greater than 1/2. So let's take a look. So this is 6x minus 3, or factor the 3 out to be 2x minus 1. For the number greater than 1/2, for example, if x equals 1, so the f double prime will be positive in sign. For the value less than 1/2, for example, x equals 0, we're going to get the second derivative that return negative in sign. Therefore, the intervals on which the function is concave downward will be negative infinity to 1/2. This is concave down. And the concave up would be on the interval from 1/2 to positive infinity. the cleaner picture after using the real number line, the hypercritical value 1/2, the right interval positive sign, left interval negative sign, concave upward on the right, concave downward on the left. So the f is concave upward on the interval 1/2 to infinity, and concave downward on negative infinity 1/2. And to suggest the graph, since the sign of the f double prime switching from positive to negative, or from negative to positive at the hypercritical 1/2. So 1/2 will give you the point of inflection. So we find the function value at 1/2 and evaluate at the original provided function, which is 1/2 to the power 3 minus 3/2 times 1/2 to the power second, and then plus 5. That should give us the value 19/4. So the point 1/2 19/4 is a point of inflection or inflection point where the sign of the f double prime changing from negative to positive, or the graph changing from concave down to concave up